All right, still on chapter 12, but now we're going to talk about what they call the moment of inertia. Everybody's seen an ice skater. Ice skater comes in, they have their hands out, they're like this, and their legs are really close together, and they're spinning on the ice, and they're spinning around. And they're spinning kind of slow, but then they bring their hands in, and so they get very tight and narrow, and then they're spinning very, very fast. Much faster than they were here. How'd they do that? Well, they didn't add any energy to their system, so they didn't speed up from here to here. What they did is they changed their distribution of mass. Now, the difference is that when an object wants to rotate, when it has to spin, remember, you have an object that's spinning, like a disc or something that's spinning around. Well, to spin that disc, you have to give that disc a certain amount of energy, or what we're going to call angular momentum. It's the momentum of spin. But when it spins, not only do you have to make the spin around it, but we have to worry about each piece of mass spinning around. And the further the piece of mass is from the center, the greater distance it has to go in the same amount of time. So it has to have more energy the further out it goes. So the point is that when you spin an object, it's not just the mass that you're spinning, it's how that mass is distributed. Okay? So it's kind of like this. If I have a mass that's a uniform disk, or I have a mass that's a hoop, which is a disk where all the material's on the outside, like a bicycle wheel, all the weight's on the outside. So they're the same mass. Their masses are equal. M1 and M2 are equal mass. But in this case, the mass is uniformly distributed, like a solid disk throughout. In this one, all the matter is on the outside of it, all on the outer edge. If you race these down a hill, the solid disk would win. Why? Because with all the matter further from the rotation point, the center of it here, it's harder to get that object spinning than it is when the matter is more evenly distributed. The closer the mass is to the rotation point, the easier it is to spin the object. Okay? All right, we call this the moment of inertia. And we write this in physics as I. Capital I means the moment of inertia. And the moment of inertia literally means how easy is it to spin an object. So whenever you're rotating something, instead of using the mass of it, we have to use the moment of inertia. And the moment of inertia, let's say we have like 3 points, 3 objects, all right? They're all connected by these massless rods, but this is M1, M2, and M3. And we want to spin it about some point in here. So we're spinning it around. So that one's spinning, they're all spinning around. Well, we have to calculate the moment of inertia of this spinning object. It's kind of a weird shape, but we can spin it like that. Well, to do that, we say that I is going to be equal to M1 R1 squared, where R1 is the distance from the rotation axis. So this would be R1. This in here would be R2. This would be R3. Plus M2 R2 squared plus M3 R3 squared. Notice this is very similar to calculating the center of mass up here. The difference is R is now squared because the distance it is from the rotation point matters a lot. Okay? Matters more than the mass does because it's squared. And so that's the biggest difference here. And for a more general thing, if you had more than like 3 particles, this becomes the sum from I equals 1 to n of M sub I, R sub I squared. Remember, R is always the distance to the rotation point. Or technically the rotation axis. In this case, our rotation axis is coming out of the page. So it's the perpendicular distance to the rotation axis. that is how you calculate I. Now, if you have an object, again, that was distributed like a blob of material and you want to spin it around a point here, then there's not all these discrete individual points. You're going to have to use calculus, and then I is just going to be equal to the integral of r squared dm, where you integrate it over the whole mass. And every single little mass point, you have to calculate the distance r to each of the points and integrate over the whole thing to get what I is. That can be a pain, as you can tell, because you'd have to know the distribution. You'd have to have this defined as some kind of function, and it would have to be defined in at least 2 dimensions, maybe 3 dimensions if it's non-uniform in all 3 dimensions. The easiest thing to do to calculate I is you look it up. In your book, you see table 12.2, which is on page 300. It lists I, the moment of inertia, for rotating around the center of mass for standard shapes, like for a disk or for a sphere. And it can be a solid sphere or a hollow sphere or a hoop. Those things are all listed in table 12.2. For a disk, I, for disk, is equal to 1/2 m r squared, where m is the total mass of the disk and r squared is the radius of the disk. So there's different ones. You look them up, and when you do a problem, that'll tell you is it a disk or a sphere, and you have to look up what I is. All right, now with the moment of inertia, when you look up I in this table, it gives I for rotation about the center of mass. However, we don't always rotate things around the center of mass. So let's say we have a disk here. So this is my 3-dimensional disk right here. So the center of mass would be the center of the disk. Okay? If I'm spinning around that, then I is just equal to 1/2 m r squared, where the radius is r. But let's say for some reason I want to do something bizarre, like I want to put the rotation axis over here. So I moved it from the center mass over to here, and I moved it by a distance here. We're going to call it the distance d. So I moved it d distance. D is the distance from the center of mass to new rotation axis. Then there's something called the parallel axis theorem. Now if you look here, the old axis was like this, so the new axis is parallel to it. It's just shifted over by amount d. Then I is going to be equal to I times the I of the center of mass, which you look up in the table, plus the mass of the object times d squared. So essentially I just becomes shifted by this amount. The center mass actually has the smallest I, which is the easiest to rotate. As soon as you shift it away from that, it becomes harder to rotate by that amount. So that's what's called the parallel axis theorem. Okay, so make sure you know how to do these to calculate what I is. And remember, this can be any number of individual points if they're all connected together. Know that you look them up in this table for typical objects like spheres and disks and those kind of things. And the parallel axis theorem tells us we can shift the rotation axis if we need to. All right, so for the center of mass and I, the moment of inertia, do problems 13 and 51.